Lecture 2. Glad you guys are still here. A few announcements to make. First of all, I'll start out with the bad news. You know, it's always good to give the bad news first. The bad news is that homework number 1 has been posted. But then the good news is that you have more than a week to finish it. So the due date is Tuesday, September 13th. I encourage you to get started early. It's a pretty long homework assignment. But it's not difficult. It's a review homework assignment. You could start on it right away because it's material you know, or material you need to review from 140. And it involves some SPICE simulation, so it's good to get all that stuff taken care of early on. And remember what I said last lecture. Maybe I exaggerated a little bit, but homework is where you learn. So if you just come to lecture, you know, I probably said 10%. You'll learn 10% of the material, but you know. It's a slight exaggeration, but there is a lot of truth to it. So the homework is very important. The other announcement I wanted to make is for those of you who don't know this class is also being webcast. And I did a little preview of the webcast yesterday, and as you might imagine, it's always horrible to hear your own voice and to see your own image. Painful as it is, what was more painful was seeing the slides, actually. It turns out the slides are way too small. The fonts are too small to see. Do they look okay on the screen? Can you guys actually see them? Okay. So I'm going to progressively try to make the fonts bigger and bigger. Should you leave something?
Here you go. Checks money.
All right. So I apologize about the fonts. The first 2 lectures I typeset them before I realized the problem with the fonts, and I try to fit a lot of material on each slide. Starting with lecture 3, I made the fonts bigger, so it should look slightly better. Also, because it is webcast, remember if you have questions or comments, use the mic. And I think your questions and comments are really important. Not only do they set the pace for the course, but it gives me an idea of what concepts are clear, what concepts are not as clear. So I do encourage you guys to ask questions. Okay, so before we start, any general questions? All right, so let's, so last lecture we started out actually part way through lecture 2. We talked about basic single-stage amplifiers, and then we moved to 2-stage amplifiers, and we talked about wideband 2-stage amplifiers. And actually today in office hours, someone brought up an interesting point. The point was, does a cascode amplifier indeed get rid of the Miller effect? So let's review that. So if we look at a cascode amplifier, the claim last week was that the impedance, so let's say we ground the gate of the second transistor, M1, M2. The claim I made last lecture is if I look up here, I see a low impedance. And I claim that you basically see, in effect, 1 over GM of 2, assuming the body of that transistor is grounded. Now, someone pointed out in office hours today that that's actually an approximation, and it's really an approximation that depends on the value of RL. So if you actually calculate, let's say, Zn at this point, a couple lines of algebra at low frequency, you'll find that the input impedance is actually RO2 plus RL divided by GM1 RO2. GM2, excuse me, RO2. And so now we can see that if we assume that RO2 is much bigger than RL, then this simplifies to approximately RO2 over GM2 RO2, which is just 1 over GM as we claimed. But if the impedance on RL gets large, comparable to RO, we can see that the impedance is still going to remain pretty low. So even for the case that RL is as large as RO2, the input impedance at low frequency is just going to be 2RO2 GM2 RO2, which is just 2 over GM, which is still a low impedance. Now, if you actually can synthesize an output impedance here that's much larger than RO, say by using cascoding on a PMOS current source, then clearly this approximation won't hold anymore. Most RF circuits work with resistive loads which are actually small relative to, let's say, output impedances of transistors. So this may be a few hundred ohms, and this approximation is valid. Okay? So thanks for bringing that up. Any questions about that? Okay. So back to the slides. Last lecture we were talking about a modern PMOS technology, and basically we talked about how channel lengths have gotten shorter and shorter to make faster and faster transistors. As a result, this overlap region has become an appreciable fraction of the total channel length. And today we have transistors which have large gate source and gate drain overlap capacitance. And that's exactly the Miller capacitance that we were talking about last lecture. Small signal model for a FET. Most of you guys are familiar with this model. Something that's easy to forget is that a MOS transistor is in fact a 4-terminal device. So it's very easy to forget about that body terminal. But in a complete MOSFET model, we have 4 terminals, including the body, and explicitly we have a generator that's excited by the bulk to source voltage as opposed to the gate to source voltage. And that's because you can think of the device as having 2 explicit gates. What are, just to review some of these basic elements, you're probably not very used to seeing gate resistance, right? In fact, you might say that's kind of trivial. Why include gate resistance in a small signal model for a FET? Because the input resistance of a FET, if we look into the gate, if it's a perfect insulator, is infinite. The resistance is infinite. You just see capacitance. So why would I worry about gate resistance? And in fact, if you calculate the magnitude of gate resistance, you find that it's actually quite small. It depends on how you lay out the device. It depends on the, let me draw a picture to make that more explicit here. So if this is my transistor, draw a 3-dimensional picture of the transistor, at least attempt to draw a 3-dimensional picture of a transistor. So this is, let's say, the drain, this is the source, and this is the gate material, and so this is the gate resistance. So let's say I make a contact here, external contact to the gate, and so I'll have a resistance which is essentially the sheet resistance of this material times the width of the device over the length of the device. And as you'll learn in other courses, namely 117, in fact, this is a distributed resistance, so there is some distributed factor. If I contact it at a single side, I actually see 1/3 of the resistance. Now, if that doesn't make much sense to you, don't worry, we'll talk about it later. The important point is that there's this physical gate resistance in the device, and, you know, because this is a function of W and L, and I can always basically program W and L, as a designer, you can choose what finger width you use for a transistor. In other words, if I have a transistor that needs a W of 100 microns, I could lay it out like this. So here is the 100 micron dimension. Here's L, which would be actually a large gate resistance, or I could lay it out as a multi-finger device. So I have multiple fingers here. Let's say 10 fingers, each of 10 microns. So I have control over this gate resistance. So the question is, why is this gate resistance even important? Up to now, you've really ignored it. We'll find out probably in next lecture or the lecture after that this gate resistance is responsible for the power gain of the device. In fact, if this gate resistance weren't there, you can get infinite power gain from a MOSFET transistor. Probably some of you have thought about that and maybe had been a little bit puzzled, right? Because if I look into the gate of a transistor, and if it's purely a capacitor, then it can't dissipate any energy on the gate side. No matter what voltage I put on the gate, it just stores reactive energy. On the drain side, though, I can extract real power. So that means that without a gate resistance, I can get infinite power gain out of that transistor. So if I want a physical model of the transistor, I have to include this gate resistance. And so this is why we're showing this explicitly on this slide. Okay, so back to the slide. I also include my source resistance. The source resistance is just the resistance of that junction. So coming back to this picture here, this source junction and this drain junction have physical resistance. This resistance is becoming more and more important because we're creating very shallow junctions. Can anyone tell me why we use shallow junctions? Why not just make the junctions nice and thick? Okay, you want to use the mic?
Is it double?
Yeah, exactly. Remember last lecture we talked about how we want the gate to control the channel. And just a physical picture is that this gate will control the channel if, basically you can think of a gate to channel capacitance and a drain to channel capacitance. Let me draw a picture. It's always easier to see a picture. So this drain is isolated from the channel, let's say in saturation, by a depletion region. But you can kind of picture this drain capacitance here, which is controlling the channel, kind of an intuitive model, if you will, versus this gate capacitance. Now, to have the gate control the channel, we want this capacitor to be much larger than this capacitor. And the way we do that is we use the thinnest possible oxide and the highest K material that we can get our hands on. For processing reasons, we prefer to use plain old silicon dioxide, but in the future it looks like we're going to have high K materials, and we can reduce the effect of the drain by using shallow junctions. So here's some nice shallow junctions, and you can see that just intuitively this transistor will have less drain control. Okay? All right, so back to the cross section and the small signal model. There are other capacitors in here. Most of these are pretty obvious. We talked about this overlap capacitance, the gate to drain capacitance. CGS is obviously Cox. It's not simply Cox, it's actually 2/3 Cox times W times L in saturation region. But in linear region, it's essentially just Cox times W times L. We also have reverse bias junction capacitances, a drain to bulk capacitance, a source to bulk capacitance here, and a gate to bulk capacitance, which is usually just a parasitic capacitance. I say it's a parasitic capacitance because ideally once we go into inversion, the gate should be isolated from the body because the inversion layer will respond to any changes in the gate voltage. So ideally that gate to bulk capacitance is 0 in inversion. More practically though, just because of layout, the gate will overlap with the body a little bit, and that physical capacitance is responsible for that. Last lecture we also talked about the output resistance. For long channel transistors, that's primarily channel length modulation, but we commented that for short channel transistors there are additional mechanisms that make the output resistance much smaller. Okay, any questions up to here? Okay, well, for most of the analysis we do here, the circuit simplifies considerably. So don't feel bad if you don't want to spend too much time with that previous equivalent circuit. I don't either. I much rather work with this simplified equivalent circuit. In this simplified equivalent circuit, we've made several assumptions. First of all, we've grounded the bulk, and in other words, we've tied, I shouldn't say we've grounded the bulk, that's misleading. I should say we've tied the source to the bulk. And if we do that, we basically get rid of this capacitor. We also get rid of this generator. Because if the bulk indeed is connected to a DC voltage, which doesn't move, then this capacitance just looks like a capacitance to ground, AC ground. And we end up with this very simple equivalent circuit. In fact, I made this big point about talking about gate resistance and source resistance, and I just get rid of them here. But what's important when you do circuit analysis, sometimes people say circuit analysis is more art than science. It's knowing when to neglect things that's important. So if someone says calculate the power gain of a MOSFET and you neglect the source resistance or the gate resistance, you'll lose. So you have to know when to include what and when not to include what. And that comes with intuition. And intuition, you're not born with intuition. Nobody's born with the knowledge on how to analyze small signal circuits. Intuition comes from practice. And so that's why I really emphasize that you need to do lots of practice. Just a side comment here. Start to think about laying out transistors. And when you lay out transistors, your interconnect is going to introduce a lot of parasitics, especially as transistors get smaller and smaller. Back in the old days, all the capacitances came from just the transistors themselves. Today, we can lay out very compact transistors with very small junctions. So in fact, the intrinsic capacitance of the device can be made very small. And often just the extrinsic capacitance, which is due often to interconnect, can really dominate. Okay. Questions or comments at this point? Okay, now something funny. You guys all know these MOS long channel device equations. In linear region and saturation region. They're very nice and simple, but they're really crude approximations. And if you take a modern CMOS device and try to fit these curves to it, maybe you did that in 105, you'll find that these are actually very crude models. And yet we use them. We use them for hand analysis. We use them for zero order analysis or first order analysis just to get a feel for bias dependencies. Certainly we can use them when we use long channel transistors, but for short channel transistors we either have to introduce artificial parameters. For instance, we have to artificially make mu a lot smaller than it is so that we get a good match, or we have to just basically take into account that this is really just a starting point in our calculations. And really the models that we use today, it's quite a sobering thought. A modern MOS model is like 3,000 lines of code, C code. So clearly you're not going to use that for hand analysis. You're going to use computer simulation. But don't give up on hand analysis. Hand analysis gives you a lot of intuition. In fact, small signal models are still valid, right? You know, these equations just describe the large signal behavior, and when you're analyzing amplifiers, a lot of times that's just the bias point. So even though you may not be able to calculate the bias point very accurately, you can ask the simulator to run 3,000 lines of code and tell you what the small signal parameters are at the bias point that you're interested in. Okay, so using these oversimplified models, we can calculate some important parameters. One of the most important parameters is the GM of the device, or the transconductance. Because ultimately, whenever we have gain in the device, we know it's related to the transconductance. Of course, the transconductance is just the derivative of the drain current with respect to the gate voltage. Drain source current to drain source voltage. Gate source voltage, excuse me. So just plugging in the numbers, we get this expression here, mu Cox, so the transconductance is proportional to Cox. The thinner we make the oxide, the more transconductance we have. That's intuitive. It's proportional to the mobility, right? The faster that the electrons move with response to a field, the more transconductance we have. It's proportional to the geometry of the device, which is nice because this is something we have control over. It's also proportional to the bias point of the device. Now, this expression is a little bit misleading, and you can play with this expression and put it into different forms. First thing you observe, if we go back to this equation here, if you look at this equation for IDS, you'll notice that when I take the derivative, this factor of 2 just comes here and eliminates this 2, and I get a term proportional to VGS minus VT. So in fact, if I take the current and divide it by VGS minus VT and multiply by 2, that's exactly the transconductance. And this expression is nice because it tells you that the transconductance is proportional to the current and inversely proportional to basically VGST of the device. But that's also misleading because as I change the current, VGST changes, or vice versa. As I change VGST, the current changes. So if I want to know what the GM is purely in terms of the current, I'll substitute for VGST in terms of the current. And finally, I have an expression which is just proportional to square root of current. So that tells you intuitively to get more gain out of the device, you have to dissipate more power. You have to put more current through your device. Given that you've sized it maximally, for instance, you've made it as large as possible, clearly the device size also comes into play, but usually you make the device large enough so that it's basically, you make it as large as you can until it starts hurting your frequency response. After that, you just have to dissipate current to get more speed out of your device. Compare this with a bipolar device, right? A bipolar device, the GM is proportional to current. So usually, if you're going for just raw gain, a bipolar device will have less current consumption. The other interesting thing is that the GM depends strongly on the mobility. So if you are making a choice between two technologies, it's always a technology with a higher mobility is at an advantage. What's interesting is because we've made our devices so small, it turns out that for the most part, the electrons are traveling at the saturated velocity. So it's not the mobility for a small electric field that really matters. It's the mobility for a large electric field. Remember, if I look at the velocity of a carrier versus the electric field, initially it's linear. That's the linear mobility, but it has a tendency to saturate. And this is Vsat. Because our devices are so small, the electric field is roughly VDS over L, right? And so L has gotten to be very small, so if we just put 1 volt on a tiny little device, we can create enormous electric fields, which put us in this region where the saturated velocity dominates. Now what's interesting is other materials, so if this is for silicon, let's say, if you look at something like gallium arsenide, it might have a curve that looks something like this. So the mobility is substantially higher for low fields. But it turns out that most materials have comparable saturation velocities. So for these very small short channel link devices, silicon is actually a pretty good material, a pretty good contender, even if you compare it to other technologies. Okay? Questions or comments? All right, let's go back to the slides. Okay, so one of the GM is a very important parameter for characterizing our devices. Another important parameter is FT, right? And FT is also known as the unity gain frequency. It's called that because FT is related to the current gain of the device. So let's draw a simple schematic here. So if I take my device and I short my output, and I inject a current, I in, I have C mu here, I have CGS here, so V in is equal to I in times 1 over S CGS plus C mu, and I out, of course, is just GM times V in, so that's I in GM over S CGS plus C mu. And so the current gain, GI, which is the output current divided by the input current, is equal to GM over S CGS plus C mu. Okay, so very simple. Notice that the output impedance of the device doesn't matter. It's shorted to ground. And this is really the short circuit current gain of the device. It's not in general the current gain, only when you short the output. Okay, so back to the slide, we see that under the simple approximation that we just made using the simple small signal equivalent circuit, this is the current gain, and if we now want to find the frequency at which the current gain goes to 0, we just set this expression equal to 1, 0 dB, or unity. We can now solve for omega t, in other words, the frequency where that goes to 1, and it's just simply GM over CGS plus C gate to drain. Now, what's the big deal about omega t? Why is it that we use omega t so much? Well, as you analyze more and more circuits, and especially if you look for fundamental limits, if you're designing an amplifier, and it's a broadband amplifier in particular, if you calculate its bandwidth under the optimal conditions, often you'll find that the best bandwidth you can get out of a device is basically proportional to omega t. More importantly, what you'll find is that approximately for a lot of amplifiers that are in some ways optimum, there's a gain bandwidth trade-off. So, and that gain bandwidth trade-off is usually bounded by the omega t of the device. So this expression here tells me that if I want a gain of 1, then yeah, I can get a lot of bandwidth out of my device. And that bandwidth is the omega t of the device. So if someone says I have a transistor, its omega t is 10 gigahertz, you know that if you get a gain of 1, you can get a bandwidth of 10 gigahertz out of it. If you want more gain, if you want a gain of 10, you're only going to get 1 gigahertz of bandwidth. So that's a very powerful first order information when you're designing amplifiers to know that. Okay, questions or comments? Yes, there's a question.
The gain bandwidth equation in here, the gain, voltage gain or current gain?
Good question. It turns out that this can be the current gain or the voltage gain or transimpedance or transconductance. This is not a truism. It's only approximately true. And we'll see that as we analyze a few amplifiers. It's just a back of the envelope kind of intuition that you get. Now remember, when you analyzed the feedback amplifiers, you also found that this was true, right? You had a trade-off between the gain, the bandwidth, and the unity gain frequency. So this is really a related concept. Okay, so if we actually substitute long channel expressions for GM and CGS, for simplicity, let's just ignore C gate to drain. Let's say it's some fraction of CGS. So we could always change this term here from 2/3 to 2/3 plus some factor. We can see that the W actually cancels out from these equations, so that the omega t of the device has nothing to do with the width. It's independent of the width of the device. On the other hand, you can see that it's a strong function of the length of the device. So these L's multiply and we get ideally a 1/L squared dependence. And it's also, interesting enough, the C-ox term cancels out, so it doesn't matter how thin we make our oxide, at least apparently so. We'll talk a little bit why that's not quite true. But to first order, we have an expression that tells us to make a faster transistor, there's really only a few things you can do. You can enhance its mobility somehow, you can make it shorter channel length, and you can bias it appropriately. That's it, basically. You can't do anything beyond that. This 1/L squared dependence is a little bit misleading. Why is that? Okay, it turns out that, again, when we look at the velocity saturation region, if we assume that all our devices are traveling essentially in the velocity saturated region, then this expression, if we simply rederive this expression, if we assume the current in the device is Q, the inversion charge, times mu times the electric field, then we get this original long channel equation. But if we assume that mu times electric field is roughly Vsat, then we just have Q inversion times Vsat, which is a constant. If we take a derivative and substitute, we'll find that this breaks down to 1/L dependence. So that tells us, it's kind of bad news. It tells us that as we scale our transistors into deep submicron regime, the benefits in speed are not going to be like square L. They're going to be like proportional to L. Still good, right? But not as good as you expected. Questions or comments? Let me go back a couple slides and say another thing about GM. If you look at this expression here, you can think, what can I do at constant current to improve the transconductance? Why do I say constant current? Because usually you have some kind of current budget. You're designing an amplifier and your boss says, hey, you've got 2 milliamps. Do it with 2 milliamps, right? And you can't go over 2 milliamps. So you say, okay, I'm going to put all that current into gain. Well, what can I do now to make my device have higher and higher gain? Right? It's obvious. Make VGS minus VT as small as possible, right? What's wrong with that logic? Yes, in the back?
You have problems with basically the process that it acts less like a transistor, or
That's right, yeah. So basically, this is something that you'll look at in homework 1, but this is a little hint. What happens to the device when VGST becomes very small? Well, you actually you leave the saturation region, the velocity saturation region. Your transistor effectively stops behaving like a MOSFET, starts behaving more like a bipolar transistor, and you get subthreshold behavior. Now, subthreshold behavior is great. It has really good transconductance because your device is acting like a bipolar transistor, but the FT of the device goes down dramatically. So the frequency response of your device becomes dismal. So that's why you can't arbitrarily decrease VGST. Another reason is you're going to have process variations, right? VT is going to vary as a function of process. So if you make VGS too small, you're going to get more process variations in your device. Okay, so now let's talk about bipolar devices. Some of you may think that we're crazy to look at bipolar devices. Bipolars are kind of like dinosaurs in some of your minds. You know, when I took electronics, we thought we were thinking about vacuum tubes in the same way. You know, yeah, vacuum tubes, whatever. We never use them. It's always bipolar devices or CMOS devices. Bipolar devices are important for several reasons. First of all, they have really good performance. So if you're going to design a very high performance amplifier and you have a choice between bipolar and MOS, you would go for bipolar. Another reason that bipolars are important is they've actually made quite a comeback. And the reason they made a comeback was if you compare a bipolar transistor speed to a MOS transistor speed, bipolars were always faster because their speed was determined by the base width. And the base width, as we can see here in this cross section, this is, let's say, an NPN transistor. This is the N emitter, this is the P base, and then this is the N collector. That base width here is determined by basically the difference between two diffusion regions. So I have this P plus diffusion region, and then I have this N plus diffusion region. And by just engineering the diffusion region growth, I can make my base width really small. And if I make my base width really small, I can make a really fast transistor. Just like we derive an equation for Ft being proportional to 1 over L squared, you can derive an equation that shows that the Ft for a bipolar goes like 1 over W squared. Now, L, let's say 10 years ago or 20 years ago, was a dimension determined, not a vertical dimension like this, it's a lateral dimension like this, which is determined by lithography. And lithographic limitations were always such that you could always get much smaller W's than you could L's. So bipolars were faster. Well, that's history. Today we can, with lithography, we can make dimensions which are very small, sub 100 nanometer, tens of nanometers, even nanometers. So that argument is gone. You can't really make fast. You can't say bipolar is better because the channel length can't be smaller than WB. Bipolars are still advantageous, though, because, and in fact, they're actually still faster for several reasons. One of them is introduction of germanium into the silicon process. So most high-speed transistors today are not simple silicon bipolar transistors. They're actually silicon germanium heterojunction bipolar transistors. And one of the beauties of the silicon germanium process is it lets you dope the P region and the N region both very heavily without adversely lowering the performance of the device. Remember, in a standard NPN transistor, what we want is the emitter injection to be much larger than the base reverse injection. In fact, the beta of the transistor is directly proportional to the ratios of the dopings for exactly that reason. And so in a regular transistor, what we do is we heavily dope the N region, but we can't heavily dope the P region or the base region. As a result, in a regular transistor, this P region can be quite resistive. And you can see now that, especially if I make the base width very small, the current component that has to go all the way to the edge of this transistor is going to experience a lot of resistance. Well, in a germanium process, silicon germanium process, I can make this also P+. and because I have a heterojunction, there's a natural barrier for holes to cross this junction. And so I can still produce a good beta transistor that has a very small RB. And again, RB is just as important as RG is important, as we'll see later on in future lectures. Okay. Okay, so going off on a little bit of a tangent here, I expect that you guys probably are less familiar with bipolars. You've probably spent a lot more time working with CMOS devices. So if you look at the lecture notes that I post online, I give you guys some reading material. It's actually quite intimidating. It says, read chapters 1 and 2 of Gray and Meyer. Read the sections that you need to review. But I do encourage you guys to review bipolar transistor physics. But the other reason, to study bipolar, even if bipolar transistors go obsolete, there's another good reason to study bipolars, in that the device physics are quite beautiful. It's just fun, and we should do things for fun once in a while. But more seriously, the type of physics that we see in a bipolar transistor are really due to statistics of basically carrier concentrations, Boltzmann statistics, Fermi-Dirac statistics. And these kinds of statistics are not going to go away. Even if bipolar technology goes away, these kinds of statistics are fundamental to nature. And it's very likely that if somebody invents a new nanotransistor, these statistics will come into play, even more so for nanotechnology. And so understanding how a bipolar transistor works is going to give you a lot of insight into the future of technology. You can think of a bipolar transistor for you guys as working with your left hand. You're not as adroit working with your left hand, but certainly if you lost your right hand, you could work with your left hand. And in fact, your left hand would become a lot better than at some point it would hopefully be as good as your right hand was. Anyhow, think of the bipolar transistor. For me, the CMOS transistor is my left hand. For you guys, it's the bipolar. Be ambidextrous. Be able to work with both hands, and it will be an advantage to you later in life when all of a sudden a new technology comes out. It's very likely that it's either going to be MOS flavored or bipolar flavored, and having both, having experience with both flavors of transistor will give you a big advantage. Okay? Yes, Al.
So bipolar transistors look just like subthreshold CMOS, and if you want to do low power design, you're in subthreshold CMOS. So knowing bipolar is great for that as well.
Okay, I'll repeat Al's comment. A very good comment. So Al's comment is subthreshold CMOS looks just like bipolar. So in effect, if you want to do low power design, you have to know how bipolars work. Thanks, Al. Okay. Any other questions or comments? I know it's painful to go back and relearn some of these physics, but it'll pay off. All right, now it's a lot less painful to just analyze circuits with bipolars because, in effect, small signal model is another small signal model. They all look the same. In particular, if we look at the small signal model for a bipolar, it's in fact simpler than a MOS because there is no fourth terminal. It behaves a lot like a three-terminal device. You can get technical and make it a four-terminal device. Let's not do that. The origin, the physical origin of these terms like C mu are now a little bit different. C mu is not an overlap capacitance, and in fact, it's a base to collector junction capacitance, right? It's a reverse bias diode, and so it's not a linear capacitor. In fact, the higher the collector voltage, the more reverse biased, and the smaller that capacitance. So I can minimize base collector capacitance, or C mu, by biasing the device with a higher and higher voltage. Of course, at some point I have to stop doing that because the junction will break down. C pi, in particular, has two components. And one component of C pi is just a regular junction, but it's a forward bias junction, right? The other component of C pi is sometimes called a diffusion capacitance, and it's related to the amount of time minority carriers spend in the base of a transistor. And for that reason, it's also related to the time it takes for a minority carrier to cross the base. So a minority carrier is injected, let's say, from the emitter, and at some point it's collected at the collector. If it's lucky, if it's unlucky, right, it ends up recombining with a hole. But if the base is sufficiently small, then we know that most of the electrons, in fact, or most of the minority carriers in general, will be collected, and that time that they spend in the base is called the forward transit time. Forward because we're operating the device in forward active region. Remember, bipolar transistor is symmetric. We can also operate it in reverse active region. So C-pi has two components, and we'll see shortly that in a lot of high-speed circuits, it's the diffusion capacitance that dominates. Now, R-pi is related to the fact that a bipolar transistor always has base current. Unlike a MOSFET, there's always current going into the base. And in RF circuits, that's not as much of an issue because it turns out that in a lot of applications, we can neglect this R-pi. And we'll see that in the next slide. Actually, 2 slides. Okay, so as I already mentioned, the large signal characteristics of a bipolar transistor are related to Boltzmann statistics. And for that reason, we can describe the current to voltage characteristics of a bipolar transistor very accurately with this equation, which is just an exponential function. And in fact, if you plot the magnitude of current over several decades, from tiny currents, picoamps, to basically large currents, milliamps, hundreds of milliamps, amps, you'll find that this exponential characteristic is more or less satisfied over an enormous range. That means that as a large signal device, bipolar transistor is very precise. We can rely on its characteristics. Whereas a MOSFET, we saw that its characteristics are very nebulous. We need 3,000 lines of code to really capture the characteristics of a MOSFET device. But a bipolar device, we just need a few equations. That's actually a big advantage. We'll see that later in the course because we're going to exploit the large signal characteristics of transistors to build nonlinear circuits. So if you don't know what the nonlinearity is, it's kind of hard to rely on it. Also, if we look at the GM of a bipolar transistor, we can see that it's proportional to the current divided by a constant voltage, which is kT over Q, or the thermal voltage, which is about 25, 26 millivolts at room temperature. So you can see that a bipolar transistor has this built-in advantage in that instead of being 2I over VGST, it's I over kT over Q, which is a very small voltage. In fact, now we see the unification of a bipolar transistor and a MOS, because if we operate a MOS at a low enough voltage, it starts to look like a bipolar. Okay, what else can we say here? All right, earlier I claimed that really the equivalent circuit is even simpler than that for RF frequencies because we can neglect R-pi. And the reason we can neglect R-pi is at high frequencies, R-pi is in parallel with C-pi, and C-pi starts to dominate at high frequencies. And to convince you of that, let's just take the ratio of R-pi to X-pi, where X-pi is the reactance of this capacitor. Well, the reactance of this capacitor is just 1 over omega C-pi, so I have the product omega R-pi C-pi. R-pi, of course, is just beta naught, the beta of the transistor, divided by Gm, and C-pi over Gm is roughly the omega t of the device, right? Neglecting C mu. In fact, for bipolar transistors, it's even more true that C mu is small. So we can see that approximately R pi over X pi is beta times omega over omega t. Now, RF circuits, high-frequency circuits, usually operate at some fraction of the omega t. Let's say we're operating at 1/10 omega t. If we substitute here, we see that R pi is 10 times more resistive than X pi. And so for most, for 10% accurate calculations, which is more or less everything we do, we can neglect the effect of R pi. And so this equivalent circuit, very simple, is kind of universal. We can use it for bipolar, we can use it for FET. And so if you get over that initial bumpiness with the bipolar, then the rest is really easy. It looks a lot like a FET. Notice that this capacitance is the junction capacitance. We go back and look at the layout. We can see that this collector is actually isolated from the substrate by another p-n junction. So there's a parasitic capacitance from the collector to the substrate. And if the substrate is grounded, then that capacitance is to ground. Now, you might wonder why we create a transistor structure, an NPN transistor structure like this, right? In the textbooks, it's always a simple NPN sandwich, right? So it would seem logical to take the substrate, make a diffusion region that's N, then make another diffusion region that's P by compensation, and then make another diffusion region that's N again, and then we have ourselves a nice NPN transistor. Why don't we do that? So let me draw a picture. Okay, go ahead. No, I can do this, right? I can make a really small width here. This is NPN. I could put some contacts here, right? And I can make this width nice and small. Why is this a bad transistor? Use the mic.
Large capacitances.
No, actually, I can make this smaller. I can actually make less capacitance with this device.
In a real bipolar, the current only goes vertical, like through a channel. And
Okay.
here, multiple directions in here.
Actually, that's actually an advantage. I can get more area out of this device. That's actually nice.
There's no isolation between devices?
No, this could be a P substrate, right? And I can reverse bias this so I have this capacitance. Yes?
So you can use the CMOS technology? Or no?
What's that? No, you can use the CMOS. Meaning that this is not compatible with CMOS. Okay, that's a good point. It isn't. But even before CMOS technology came around, nobody built transistors like this. Anyone else? It's in the back?
Don't we use epitaxy to do BJT? In this case, you use ion implantation, right?
Okay.
So you can't really control the abruptness of that NPN as good as epitaxy.
That's actually not it. The real reason is I can't create a good transistor. Remember, a good transistor has electron injection dominating over hole injection, right? And in this structure here, because I have, basically I'm creating NPN materials, this N material has been compensated 3 times, right? So it's very hard to make this a heavily doped region compared to this P region. Because first of all, I have to dope this, counter-dope it to make it N region, and then I have to dope it again to make it a heavily doped N region. So I can't create an N plus P junction. And therefore, I can't create a good transistor. Now, this is why I have this different structure here. And this other structure, what I do is, instead of creating a triple diffusion region, I create a double diffusion region. So this is N plus P. And what I have to do is somehow make a contact to my collector. My collector is down here. And so I create a N plus buried layer. So this is N. So this is NPN plus. And this buried layer now makes contact to the sinker. And this is my collector. This is my emitter. This is my base. So the transistor structure is awkward because of the fact that I can't put 3 diffusion regions inside of each other. Okay. Now, in a modern process, you can play lots of tricks to try to reduce the fact that now you have this large capacitance to substrate. For instance, you could put an oxide down here, and that will reduce this capacitance considerably over a p-n junction capacitance. Questions or comments? Yes.
I'm wondering, considering the fact that, like, if you look at a MOSFET, the body, the source and drain actually looks like a BJT as well. So is that by any chance possible to take advantage of that and have a higher GM by using like a BJT MOS hybrid transistor?
Yeah, you're exactly right. That's called a lateral NPN or lateral PNP. usually the reason that bipolar devices are preferred to be designed vertically rather than laterally. Again, these are pretty advanced questions, so if you don't know the answer, don't feel bad. You know, we're just trying to get you guys to think. So let me see if anyone has an idea. Why is a vertical NPN better than a lateral NPN? Again, most of you probably will not know the answer. Don't want to discourage you from guessing, though. Yes, Jason.
Is that better to control the diffusion?
Better to control?
Say if you implement the ion on if you do the doping, it's easier for vertical and
No, so we're comparing a vertical structure to a lateral structure, right? The
yeah,
point that was made is
yeah,
that
for lateral you can't really control the source and drain diffusion.
You can.
Well,
you can control it in the same way. We're not talking about creating a bipolar in CMOS. We're just saying use CMOS techniques to create a very small channel length device, which in fact is a bipolar device. In the back?
Is it because it's harder to get the wider area of the contacts between the N and P regions, the P and P regions?
Good guess, but that's not it. No.
I guess when you try to fabricate it, it's hard to make the lens small enough. If you're doing it horizontally, if you do it vertically, you could, I guess, have much.
That's a good point,
lens.
but that's that's a good point, but it's no longer true. Today, lithography is excellent. We can make very small channel lengths. Okay.
Is it because the surface of the silicon has less mobility?
Very good. That's it. In fact, there's two things that are a disadvantage in working at the surface. The surface mobility is lower because of the so-called dangling bonds. There's an interface between silicon and silicon dioxide, and that interface is not ideal. So there's additional scattering sites at the surface, so we get a lower mobility. The other problem, now we haven't talked about noise yet, but as a preview to noise, one source of noise in all transistors is flicker noise. And flicker noise has a 1/f spectrum, meaning it gets larger and larger at low frequencies. And it's a big, big problem. When you're designing circuits, because the noise is so high at low frequencies, it can dominate the noise of the transistor. And it turns out that bipolars have much lower flicker noise than FETs. And actually, a lot of that is because the bipolar is a buried device, and it doesn't interact with the surface. It's the impurities that the surface traps that create flicker noise. The mechanisms are not completely understood. There's lots of models for where flicker noise comes from, but it's very well understood that it's due to the surface of the device. So if we create a device that's buried, it has much better noise performance. Okay, so let's move on. Talked about the exponential characteristic. We talked about how this is a generic equivalent circuit. And again, we don't need to redo the calculations because the equivalent circuit is identical. We know that the FT of a bipolar transistor is also GM C pi plus C mu over C pi plus C mu. And now if we substitute for C pi with CJE plus the diffusion capacitance plus C mu, and we make some approximations. Now we're going to assume that in forward biased region, the junction capacitance is roughly twice the junction capacitance at infinite reverse bias. Okay, not infinite reverse bias. CJE 0. Remember, the junction capacitance CJ is CJE 0 divided by 1 plus V reverse bias over phi to, let's say, 1 over the nth power. And so CJE 0 here is, so if you actually plug in a forward bias here, you can see that this expression blows up when the forward bias is exactly equal to the built-in potential of the junction. Clearly that's wrong. If you do a more exact analysis, approximately CJ forward bias is approximately twice CJE 0. Okay, so we'll use that approximation. So going back to the slide. Now the diffusion capacitance I talked about earlier, it's related to the forward transit time of the transistor. If I just substitute C diffusion, it's GM times tau F. And C mu is also just a junction capacitance CJE. Now, I can take this expression and just simplify it a little bit. I'm going to divide the numerator and the denominator by GM. And you can see that this term becomes a constant tau f, and this term simply divided by tau f. Now, if you remember, GM is proportional to current. So if I keep increasing my current, eventually this term will become negligible compared to this term, right? If this model holds, if I make GM large enough, then the omega t of the device will approach 1 over tau f, as I've shown here. And so if I were to plot the ft of the device, then as a function of the current, you would expect it to have a shape that looks something like this. And you would expect it to saturate out at this dotted line, which we call, basically, which is just determined by the forward transit time of the transistor. It's a very nice intuitive result. It tells you that fundamentally the transistor can't respond faster than the time it takes for carriers to cross that base junction. Now, in reality, if you go out and measure a transistor, and many of you did this in 105, you'll find that unfortunately, instead of just saturating out like this, it starts to drop. Okay? Does anybody know why the FT drops at high current levels? It's not because of Star Trek, right? This is not Captain Kirk. It's another Kirk. Well, this Mr. Kirk, or probably a Dr. Kirk, explained this effect, and it comes from when you analyze a bipolar transistor, we make a low-level injection assumption. We assume that the current level, basically the minority current injection, is much smaller than the background carrier concentration, and so then the equations all simplify. If you have a high-level injection condition, which happens at high current levels, the doping levels, basically the minority carriers are so numerous that they effectively can change the typeness of the material. In other words, they can make the base grow out, and so we call this base widening. And as the base grows out, the transit time goes up, and that's why the FT of the device suffers at high frequency. Now, the reason I show you this curve is not so much that you understand the physics of it, but this curve tells you exactly the optimum point to bias your transistor to get the maximum performance. It tells you that if you assume your circuits all respond like the FT, in other words, if I make the FT faster, I can get more bandwidth out of the device, then I should make the current just large enough until I hit this peak point. Okay? Questions or comments about that? All right, so enough talk about device physics. Let's start looking at some circuits. I wanted to back up the claim that omega t is important. So the first circuit we'll look at is a very, very simple circuit. It's basically a current amplifier. But it's a current mirror, right? A current mirror, though, is a very important circuit, not just for biasing circuits, but also because it has the property, a unique property, which we'll see, that the input-output relationship is actually linear, large signal and small signal, as long as devices are not driven too deeply. So we'll come back to that point. First of all, let's calculate the current gain from the input to the output, right? That's trivial. This is a 1 to n mirror. I've made this device n times larger than this device. If I assume that current is just a function of VGS, right, then because this looks like n transistors in parallel, it should have n times the current. So without doing any math, I would expect that this device, the current gain here, should be n at low frequency. Well, I'm not concerned about low frequencies. I'm concerned about high frequency. I want to see what's the bandwidth of this amplifier, because it looks very promising. It looks like this is a nice way to build a current amplifier. And the reason it's promising is that it has a very low impedance. Because this transistor here is diode connected, it sets the impedance of the circuit to roughly 1 over GM. And the capacitances in this circuit are proportional to basically C pi, right? It's the C pi of this device plus the C pi of this device. So to first order, I can see that the bandwidth is going to be something like omega t. All right, well, it takes a few lines of algebra to verify that. I'll substitute this with an equivalent circuit. On the right here, I have the equivalent circuit of this transistor. We'll call this transistor 2, which has n times the GM of transistor 1. Consequently, it has n times gate to drain capacitance, and it has n times the CGS. To find the current gain, I'm going to short the output. Again, this is a good assumption as long as the load impedance is relatively small. I short the output, RO doesn't matter, right? Now, this diode-connected transistor degenerates to a very simple model. It degenerates into a capacitance in parallel with a resistance. And that's because VDS is equal to VGS, right? And so if I change VDS of this device, it directly changes VGS and changes the current of the device. So this thing looks a lot like a resistor. If you're not convinced, draw the equivalent circuit and play with it, and you'll find that, in fact, this is the correct model for the diode-connected transistor. So this is so simple that we don't even need to write it out. The output current I out small signal is equal to GM2 times VGS, and VGS is simply I in times this impedance, right? And or 1 over this admittance, neglecting C gate to drain, okay? I'm going to make a simplifying assumption. Now this admittance here is also very simple. It's this GM plus this capacitance, which is just SC in, and then this capacitance, which is N times SC in, or C pi if you like. And so the total gain of this circuit is, if I divide numerator and denominator by GM1, it's GM2 over GM1 divided by basically a pole. Simple transfer function has one pole. And the pole we can see is N plus 1 times Cn divided by Gm, and Cn over Gm is just omega t of the device. And GM2 over GM1, well, that's just N, right? I have N transistors in parallel. So here is the total transfer function. The gain is N at low frequency, just as we predicted. And it has a pole that is basically omega t of the device divided by N plus 1. So now if I take the gain of this device and multiply it by the bandwidth, I have the gain is N, the bandwidth is omega t divided by N plus 1, and you can see that this is roughly just omega t. So in fact, this amplifier behaves in this nice way that the gain and bandwidth trade off and give us a pole at omega t. Any questions about that or comments? Now, at the very end here, notice I say that this device is large signal linear. What does that mean? Let's just review what that means. Okay, so let's come back here. And let's review the concept of small signal and large signal. This is a generic device. It could be a bipolar, it could be a FET, it could be some arbitrary device. And what we've done in other courses like 140 and 105 is we've linearized this device. In other words, we've observed, let's say, some output current, I out, is some nonlinear function of, let's just say here, V1, and let's just say V2 here. Okay? So this relationship is called a large signal relationship, because it's true no matter what the magnitude of the signals are. Now, in other courses, instead of dealing with these ugly equations, these nonlinear equations, we linearize the circuits. And the way we linearize circuits is we assume that we operate at some quiescent point plus some small signal voltage. And we've made the argument that if these voltages are small enough, we can do a Taylor series expansion. So I can partition the output into a quiescent output current plus some small signal current, And if I do a Taylor expansion on the right-hand side, I have f of v1q, v2q, plus v1 derivative of f with respect to v1 operated at v1q, plus, let's just say v2, derivative of f with v2 operated at v1 and v2 quiescent. So this is 1, 2, this is 1, 2. Okay? And if you look at this equation, the right-hand side and the left-hand side, we can see that this and this cancel out. And so that I out is just, let's just say, alpha 1 v1 plus alpha 2 v2. Now this is exactly the small signal equivalent circuit that we work with. And this is a linear relationship. And this is only valid for, in the limit, for extremely small signals, right? Because what we've done is we've neglected the higher order terms. And those higher order terms become important as the signal levels become large. So in this class, we're going to spend a lot of time worrying about those higher order terms. But what's interesting about this current mirror is that the small signal model and the large signal model are in fact the same if we assume we're operating everything in the saturation region. So if this transistor by definition operates in the saturation region because its VGS is equal to VDS, right? This transistor could be in the linear region or it can be in the saturation region. So if I assume that the output voltage, which is equal to VDS, is larger than VGS minus VT, then this transistor will operate in saturation. Now, the idea is that the IDS of this transistor is equal to this input current. The output current is some nonlinear function of VGS. And also the output, right? Because it has finite output conductance. But let's neglect the output conductance, okay? So if I now look at VGS, VGS of this device is equal to VGS of this device. They have the same VGS. And if the nonlinearities in these transistors are the same, the VGS of this device is the inverse function of the input current. And so now you can see that the output current is the function of the inverse function of the input current. In other words, it's proportional to the input current. Now there's some scaling going on because these transistors are not the same size. This would only be true if the transistors were the same size, but I leave it as an exercise to you to go and scale the devices and show that this is true. In fact, it's quite trivial. You can just imagine scaling is having n transistors in parallel. Then this calculation is true for one transistor. The output current should be n times this current. And you can see that the input-output relationship is large signal linear. Okay. This is also interesting because internally the device is acting very nonlinearly. The relationship between VGS and the input current is a nonlinear one, but the overall input-output relationship turns out to be linear. Okay, questions or comments? All right, so we have a little more time here. We can start lecture 3. And for the next several lectures, we're going to focus on high-speed amplifier design. And initially, we'll use our techniques that we've learned in 140, but soon we'll migrate to some new techniques which come from analyzing general two-ports. So they're very general relationships that apply to any kind of two-port systems. Okay, so let's verify some of the things that we said last lecture. Last lecture we said problem with a common source amplifier is Miller multiplication. And so here let's do it a little more quantitatively. If we assume that that this system has a dominant pole, let's say at the input, then the pole is simply Rs times the equivalent input capacitance looking into here. The equivalent input capacitance, of course, is just C in plus the Miller multiplied capacitance, AV times C mu. And if I basically pull Cn out of this equation, I have 1 plus mu times AV. And as I mentioned before, mu is basically C mu divided by C in. It's a dimensionless number. In modern technology, this can be as large as 0.5. In other words, 50% of the capacitance. In the good old days, this was like 2%, 5%. Nowadays, it's 30 to 50%. So mu is actually quite large. And if the voltage gain is, let's say, larger than 2 or 3, then this term starts to dominate. And so we can see that the pole is actually proportional to the voltage gain. Okay. Now I can rewrite this pole as basically I can multiply and divide by Gm. And so here I can identify Cin over Gm as the omega t of my device. And I can identify GMRL as a low frequency voltage gain. So if I multiply this by RL over RS, then I get voltage gain squared times RS over RL times the omega t of my device, 1 over omega t times mu. In other words, if I try to write this as this is the bandwidth that I'm getting, assuming that the input bandwidth is dominating. Remember, this is a dominant pole approximation. The input bandwidth, omega, so if I now invert this equation, I have a simple relationship which tells me that the bandwidth times the voltage gain squared is proportional to some factor of omega t, right? And now we can see that this amplifier is actually not such a good amplifier because of the fact that the voltage gain here is squared. Let's take an example to see why this is a problem. Let's say you're trying to design an amplifier with 60 dB of gain. That's a lot of gain, right? So it's an example. It's an exaggeration, but it makes a point. And let's just say that RL over RS is a factor of 2. And let's say that our technology gives us a mu of 20%. Okay? So now if I take omega naught, the bandwidth, times the voltage gain squared, I have 10 to the 6, which is 10 to the 3 squared, times omega naught. Gotta stop tapping the screen here, which is equal to omega t times 2, which is this ratio, times 5, which is 1 over mu. In other words, the bandwidth of this circuit is omega t divided by 10 to the 5. That's a huge bandwidth shrinkage, right? Compare that to the current mirror that we just analyzed. The current mirror we found has a current gain which goes linearly with bandwidth trade-off. So there, for a gain of 1,000, my bandwidth would be 100 times better using the same transistors. So, in other words, high-speed amplifiers have the property that their bandwidth is usually set by gain times bandwidth equals to some fraction of omega t. So if you're ever looking for good amplifiers to use for wideband application, look for that property. Let's compare that now to a common base amplifier. Okay, so simple common base amplifier shown here. I have some source resistance, I have some load resistance. Current gain is equal to 1, but I get a voltage gain of roughly RL over RS, or degenerated GM times RL. Okay, so let's analyze this circuit. So here's the equivalent circuit. Notice that I'm neglecting R-pi, excuse me. I ground the base here and simply apply a voltage here. Doesn't take Einstein to solve these equations. They're very simple. Let's do KCL at this node here, at the input node. The current going in here is Vs minus Vin, or plus Vin, over Rs, plus this current which is coming in, which is Gm times Vin, plus this current, this capacitive current, which is coming in, which is Scin times Vin, and let's neglect this current. Let's assume Ro is pretty large. I can do that. We'll come back to when you can do that and when you can't. So now I can solve for Vs in terms of Vin. Vin is this voltage here, and it's this simple relationship. Okay. Now writing KCL at the output, it's a little bit harder to see here. There's basically a V out over RL term. There's a GM V in term again. There's a V out SC mu term. And there they are. So this is I added an output capacitance to make the expression a little more general. So this is essentially, this is the GM current, and this is the feedback current going through the feedback capacitor, which in fact is not a feedback capacitor. So here I can solve for V out in terms of V in, called it Vx here. And previously I had an expression for V in terms of Vs. So simply multiplying everything out, I have this expression. Let me write that down here. So I find that my total gain is 1 plus SC out over RL times V in over Vs. And previously I found that V in over Vs is equal to minus 1 over 1 plus GM Rs plus SC in Rs. And what I'm going to do is I'm going to divide the numerator and denominator by this constant term here, 1 plus GM Rs, divided by 1 plus C in, or 1 plus GM Rs, times Rs. Okay. So if I now simply substitute this into here, I get this final expression that the voltage gain is capital GM, positive, because these minus signs cancel out, and we know that common base amplifier does in fact have positive gain. Capital GM is equal to little gm degenerated by 1 plus GM Rs. That's the effect of the feedback at the input, divided by two poles. The first pole we might call the output pole, is due to RL, CO, and C mu, and the second pole we might call the input pole is due to RS and the input capacitance. Now we can see now that the common base amplifier is actually quite broadband. This term here looks like a degenerated capacitance. The action of the feedback is to degenerate our transconductance, but it also helps in reducing the input capacitance. So here we have two poles. The first pole is actually, let me go back here. So if I assume I have large loop gain, GM Rs is large, and you can see that Rs cancels out here, and I have just Cn over Gm, which is of course omega t. So this pole in the limit of large loop gain is actually omega t. And this output pole really depends on the load resistance I use. And the load resistance I use is basically setting my gain, right? The more load resistance I put, the more gain I can get out of this device. And so here you can see that in the limit that I make the loop gain very large, the DC gain is independent of the GM of the transistor, right? That's the action of the feedback. So the overall gain is just RL over RS. Another way to think about it is that the GM of the transistor degenerates to just 1 over RS if RS is much larger than, let's say, 1 over GM. And I have two poles. One is at omega t, and one's due to the load. And so I have total control here on the bandwidth of this amplifier. I can simply make the bandwidth larger and larger by making RL smaller and smaller. And in fact, if I make RL smaller, the gain drops, and you can see that there's a nice gain bandwidth trade-off. In the limit, in theory, I can make this very wideband, as wideband as the omega t of the device. Okay. Questions about that? Comments? Okay, so we'll pick it up there next Tuesday. Don't forget about the first homework.